When we're analyzing a dynamical system, a question that we should be pretty interested in is, can cyclical behavior occur? Can there be a periodic oscillation? And in the case of oscillation around a center, so if we have a fixed point that might be a nonlinear center and we have a phase portrait that looks like this, okay, well, that's not so hard to identify because we have the fixed point and we classify it, we learn it's a center, and then we check that the center persists even in the nonlinear case. So the case where it's hard to figure out whether this kind of oscillation exists is going to be the case of a limit cycle. And although we'll have further quantitative questions about limit cycles, such as how long does it take to get around the cycle, later on, the very first question we want to ask when we're presented with a 2D system is, can it have this kind of oscillatory behavior under some parameter set? And you can imagine this question is important because you may be analyzing some mechanical system, say a bridge, and it's incredibly important that it not have this kind of oscillatory behavior. And so you might want to be able to rule out that oscillations could ever occur in the system that you're analyzing. So we're going to start with some methods for attempting to rule out the existence of these kinds of periodic orbits, these isolated periodic orbits that we call limit cycles. The first method we might appeal to is index theory. And the reason index theory can help us think about whether there's a closed orbit is that we know that on a closed orbit, around a closed orbit of a system, the index needs to be +1. But we also know that for an index to be +1, it needs to enclose a mixture of fixed points whose indices themselves add up to +1. And so if we happen to have a system where the particular fixed points that we've identified as existing in the system preclude ever getting an index of 1 around a closed curve, then we know that there's no closed curve in that whole system that could be a limit cycle. And more narrowly, maybe we have a particular region of some dynamical system where the nature of the fixed points precludes the possibility of a closed curve having an index of +1. And so we have an example of this right here. I've sketched a system that has a single saddle node, and so the index on that saddle node is -1. And so no matter where we draw a curve, if we draw a closed curve over here, it's not including any fixed points. It'll have an index of 0, so it can't possibly be a limit cycle. And if it were to enclose this fixed point, well, it would have an index of -1, and so it also can't be a closed orbit, a limit cycle. And so index theory can be a little bit helpful in that there are cases where it can preclude the possibility of a limit cycle. Another way to preclude limit cycles is to invent some kind of interesting function that always decreases along trajectories. And so if we start at a particular point, the function has value v of xy, and then as we move forward in time, the function changes. So as we go from maybe time 0 to time t, the change in the value of the function would be the integral of dv dt. This will give us delta v as we go from time 0 and integrate back to t. So if we have a limit cycle and it takes a finite amount of time t for us to traverse it, and we start at a point, and our function has a particular value at that point, and then we integrate, and we know that whatever this function is, it decreases along trajectories, then while we're integrating, the function needs to be decreasing the whole time. And so dv dt is negative, and that means that the change in v also needs to be negative. But with the closed orbit, okay, well, we've said v needed to change negatively, but actually we get back to the same spot where we started, and so v shouldn't have changed at all. And so that would create a contradiction. And so in this kind of system, a system where we're able to construct a function v with the special property that v dt is always negative along trajectories, that v is always decreasing on trajectories, then we're able to preclude for that type of system any kind of fixed point. And so the challenge there is if we're given a 2D dynamical system, attempting to construct a function like this might be quite difficult. To construct an example of this, I'd like us to start, we're going to make a very general example. I'd like us to start with any non-constant function v of xy, and whatever this function is, we can create a system whose trajectories traverse this function in such a way that they basically that v is always decreasing along the trajectories. And so this is by construction, but then once we've constructed something in this way, perhaps we'll be able to go backwards to find v. And so given a function v of xy, if we let dx dt equal negative v sub x and dy dt equal negative v sub y, then we actually have a gradient system where x dot equals negative gradient of v. And you might recall from multivariable calculus or not that this means that we're always kind of going downhill on this function. So if this function had a hill, our trajectories would be going down it. And that by construction is going to give us v decreasing on trajectories, but let's actually make sure of that mathematically. To determine whether v is decreasing along trajectories, we want to find dv dt while we're moving under the influence of the vector field. And so that's a total derivative, and to take it requires the two partials of v, change in v with respect to x times change of x with respect to t, plus change of v with respect to y times change of y with respect to t. And I've said that we want to be moving under the influence of the vector field, so dx dt and dy dt are given by our vector field definitions. And so this means that we have vx times negative v sub x, which is dx dt, plus vy times negative v sub y, because that was dy dt, and so this is negative v sub x squared minus v sub y squared. And so you can see that dx dt and dy dt were chosen in a pretty careful way so that vx squared is positive, vy squared is positive, and these negative signs mean that dv dt is just always going to be negative everywhere on every possible trajectory of the system. And so for this kind of system, we can rule out a closed orbit. And now let's go ahead and do an example with a function. I made up some function, sine x times y, and now we need to define the dynamical system, and x dot is supposed to be negative v sub x, so I need to take the derivative of sine x, which is cosine x, and so this is y cosine x, and I forgot the negative sign, and then I need a negative sign here, and the derivative with respect to y is just going to be sine x. Okay, and so here's a system, and it's what we call a gradient system because it came from taking the gradient of this function. And we know for this type of system that dv dt is equal to negative vx squared minus vy squared, which is equal to negative y squared cosine squared x minus sine squared x. And so this quantity is always going to be negative, and closed orbits are not possible. If we are given an arbitrary system and we want to check whether it's a gradient system, that's also something that we can do. So if we want to check something is a gradient system, which means x dot is negative times the x derivative of some function and y dot's negative times the y derivative of some function, we can check that the mixed partials match. So the change with respect to y of x dot should be equal to the change with respect to x of y dot, and that's because negative v sub x sub y should be equal to negative v sub y sub x. So we can check whether this condition holds, and if it does, the system we're working with should be able to be expressed as a gradient system, and we can preclude limit cycles and closed orbits in that case. So far, we're in this situation where we have option 1, use index theory, and option 2, create a decreasing function. Create a decreasing function. And this function generally is called a Lyapunov function. And so these are two options we currently have for ruling out closed orbits. Maybe index theory, maybe we can create a function that always decreases along trajectories, a Lyapunov function. That's really hard to do, but potentially we can do it. And there's one more common option for attempting to rule out closed orbits. In this third method, we use Green's theorem, which relates an integral around a closed loop to an integral over the area inside the loop to draw a contradiction that then implies that there can't be any closed orbits in a particular system. Green's theorem says that if we take the integral around a closed loop of some vector function dot the normal vector ds, then it's equal to the integral over the enclosed region of the divergence of that function. And I'm going to draw the normal vector on. So this is the normal vector. And we're going to make a choice of function. Let f equal g x dot. So g is some kind of scalar function, and x dot is our vector field. And so that creates a vector function f, but it's a really specific vector function f because it's always pointing in this direction, tangent to the vector field. And so this function by construction has the property x dot n is always 0, and this function has the property that this integral is always going to be 0. And so the way that we're going to draw our contradiction is we're going to say, okay, well, if this kind of function exists, where we always get a 0, but we're able to choose g so that this thing on the other side is negative, then it's like not ever possible to have an equality here, and thus there actually can't be any closed loops in this system. And so our goal is, given the vector field, we need to find some function g so that this expression is always negative, and we know that this side of the integral will be 0, and then we would be, this theorem says that we have equality between a 0 and a negative number. Not possible, so no limit cycles exist, leaving us kind of the crazy challenge of figuring out how to find a g so that this quantity is negative. This method of ruling out closed orbits is called Dulac's criteria. So the upshot of this method is that we need to construct some g so that this divergence is less than 0 everywhere in a region of interest, and then we can use this argument via Green's theorem to argue that there can be no closed orbits in that region. And there's an example of this in the book, but it's really not clear how to construct these functions g, and I would guess that it just takes a ton of trial and error. So that was option 3. Option 3, Dulac's. Okay, and so we have 3 basic options for attempting to rule out some kind of closed orbit, some kind of periodic orbit existing in our phase space. And the next thing we'll look at is whether there are any ways to argue that a closed orbit must exist in some region of the phase space.